Now for our last talk, an incremental algorithm for algebraic program analysis by Chenyu Zhou, all right, from University of Southern California.
Can you hear me now? Okay, just put it here. Don't touch it. Oh, yes, thank you. So thank you for introduction. I'm Chenyu, a second-year PhD student from University of Southern California, and this is a joint work with Yuzhou, Jingbo, and Chao. Jingbo is from Purdue University, and the rest of us are from University of Southern California. In this presentation, I will propose a method for efficiently compute the incremental result of algebraic program analysis. I will start from introducing the background of APA and the incremental analysis, and also why this task is important. The APA will involve a clean algebra system into the program analysis. The APA does not replace abstract interpretation, but finds another way to compute that. Many useful algebraic properties from the clean algebra system could be helpful in our analysis, and it will be easier for us to handle the large-scale, parallel, incomplete, and also the incremental analysis. Also, the algebraic system will enable a non-iterative way to compute the result of algebraic program of abstract interpretation, which will also be useful in some quantitative tasks. So in our work, we will mainly focus on incremental analysis. The incremental means that if we already have a program P, just like a program on the left, and also we made a small modification to make the program on the right as P prime. The problem is, can we efficiently compute the analysis result without recomputing all the things from scratch? To figure out this solution, we need to start from a general workflow of APA. So the APA is different from the iterative-based analysis, especially in data flow analysis. It will first compute a past expression row, and then involve the data flow facts into the analysis. So the first step will only explore the structure of a program. Notice that the past expression is as a regular expression, so there are many space for us to do some rewrite or do some transformation based on the analysis task we want. And also, after that, we can define our abstract domain based on the analysis task, and then interpret the past expression into the abstract domain. After the interpretation is finished, we can see the final program facts of row, which is the analysis result as we want. So here, let me give us a very simple example. Let's assume we are required to perform an uninitialized variable analysis. I think everyone here knows how to do it, right? So now let's take a look at how to solve it in APA. First, we need to define a clean algebra system, which contains a symbol set A, 3 operators, the plus, the multiply, and the star, and also two special units, the two elements, the 0 element and unit element. Then we define abstract domain as two sets, the possibly uninitial sets PU and the definite initial set DI. Also, we need to define a semantic function D to map in the program into the abstract domain to store data flow facts. After that, we will define interpretations of the 3 operators, indicating that if we miss them in the past expression, what we will do for them. So let's see how the APA will compute the analysis result for a program. Here, the red one is a possibly uninitialized set, and the blue one is a definite initialized set. So let's look at line 2 and 3. In line 2, we got this result, and line 3, we got this. So when we use the multiply operator to combine them together, we'll get this result according to our rule. Similarly, when we have a line 6, 7, and 8, we'll get this initial information. And also with the plus operator to combine them together to get this. Then we multiply with 9, 9 to get this one. After this one, we'll make a loop. So whenever we make a loop, we'll use the star rule to get an analysis result. So that's actually how the APA will perform program analysis based on this kind of program. When it turns to incremental analysis, the situation is a little bit different. So comparing to the previous program P, here we add a new line of code E2 into the P to make that P prime. So since we already modified the program P, well, the past expression row will also be changed as row prime. It has a new letter on that because we add a new line of code here. So because the past expression also changed, the interpretation result will also be changed. So this is how the incremental changes could affect the APA process. But previously, the key idea of APA is that we have separation over these 3 parts. The computing that past expression and the computing depth of facts, they're all separate. They do not know each other. This idea enables many optimizations and design tricks on different kinds of analysis. But in our incremental task, this feature becomes an obstacle in our path, as recomputing both of them fail to make use of the previous information. So the challenge is, so how can we efficiently organize this result and reuse this information to mostly reduce the recomputing? Oh, sorry, okay. To solve that, we can also make one step deeper into the problem. So actually, the path expression is maintaining the program structure of the CFG. If you do some modification on the program structure, actually you are dynamically maintaining a CFG. We all know that dynamic graph problem is not easy. So it's impossible for us to just find some textbook and find some graph algorithm to directly solve that. So therefore, to tackle this problem, we need to start from the program itself and to see if the algebra and the semantic could help us to do so. Our method tries to use the previous analysis result and reduce the recomputing. So the main goal is that we want to make the most use of previous information as much as possible. To solve this, we must figure out how can we better organize the information on the graph, and also how can we involve previous information inside our analysis. This problem drives us to explore the properties of clean algebra system, and finally we find that the associativity rule of clean algebra system could help us develop our algorithm. But how to make use of that? So let's come to the second part of our talk, motivation. So here, if I just give you a path expression rule and the interpretation, actually we already redefined the plus, the multiplier, and the iteration, and also we redefine every element. Actually, we're redefining arithmetic. So the most straightforward idea is that we use a computer direction, define two stacks from operand stacks and operator stacks. We scan the path expression, and after the scan, we can compute the result of this path expression. Actually, everyone is familiar with that in a real number system. But however, though this idea is very straightforward and elegant, but it fails to be incremental. Let's say if the path expression becomes a row prime and the interpretation also changes, we cannot retrieve the stack within this situation, so it cannot be incremental. So how could it be incremental? So here, let's build the expression another way. Let's see if we already get the interpretation result of E1. So let's say we're adding an E2 to a row prime, and very luckily, we already get the result of E1 and the rest of our part, and we store there somewhere in our computer. So if we want to insert E2 between them, actually we only need to do 2 computations. Then we'll get the result. It's very fast, right? But actually, we are not always that lucky. We are not always lucky enough to precisely split the expression and where the future incremental will happens. We are not fortune teller, right? So we cannot do that. So if very unluckily we split the program in a wrong way, it will not help us do incremental. So we need to find a better split of expression so that we can automatize the computation to make it faster. And then we also find that the change in the computation order will reduce recomputing. That's why we can scale better split of expression. This brings us to our third part, our method. So we use a normal APA process as a baseline, and then add 3 innovation solutions for the challenges mentioned earlier. So for challenge 1, we use a data structure to update and pass expression along with the interpretation together. For challenge 2, we design a tree structure to efficiently maintain the program facts. For challenge 3, we categorize the incremental changes into 3 basic operations, and design methods to handle them. These 3 new components are our main contribution. I was going to introduce it one by one. So the first one, let's look at how we can update the program facts and the path expression together. So we can find that the interpretation is bundled with the path expression. And very luckily, we can find that every interpretation we maintained with APA also satisfies the rules and invariants in the clean algebra system. So with this property, let's see how can we do this for the program. We designed an APA tree to maintain such path expression. So every leaf node here is the actual CFG node or actual letter in the path expression. And every branch node is an operator, like multiply, the plus, or the star. The number of its branches is decided by the operands it has. For example, the multiplier has 2 branches, and the star only have 1. Besides that, we want the tree structures to be as balanced as possible. And also we can find that this tree is a valid expression tree of the initial path expression. But we all know that the expression tree could not be the only one, right? So we want to be as balanced as possible. By recognizing the program into this structure, we will find that we will remain most of the parts to be unchanged when some incremental changes. Now the problem is, the tree looks very beautiful, right? But how can we build such a tree? Let's start from a simplest version of the program. So here let's consider the program straightforward without branches and loops. So it's very easy to build a complete binary tree to replace this program. It's very balanced. So when the program becomes a little bit complex, it has branches. To build a valid tree, we must first handle the 2 branches, then put a plus operator on top of them. Also, in the same way, we can handle the loops. For the loops, we first need to tackle the loop body, then put a star in front of them. So by doing so, actually, we are figuring out a way to linearize a control flow graph into such a tree structure. To summarize the previous process, we were identifying these 2 basic structures iteratively from the program, the loop structure and the branch structure. We scan the whole program to see if we can find them. Once we find them, we'll shrink them into one line, into this one edge. Notice that when we made multiple nodes gradually connect together, like if we already shrink a node, we also need to shrink them into one node. By iteratively doing so, finally the program will have only one edge. Then the tree building will process. Whenever we do a shrink, we will build a subtree into our initial API tree. Finally, we will connect all the forests together to get a one valid API tree. So let's come to the third part of our talk. After we build such a tree from the original program, how can we handle incremental changes? To solve this, we need to first identify these changes. We categorize them into 3 basic categories. In baseball level, we can view that as edit a basic block, delete a base block, and update a base block. We notice that the add and delete, they are structural changes. Means that by doing so, the control flow graph structure will be changed. And also the update one will only influence semantic, will not influence the program's control flow graph. So that's from the easiest one, the semantic changes. Let's see how we can handle the update queries. Since there's no influence on structure of the program, the tree structure always remains the same. So first, we'll locate the expression. Let's say if you want to modify the E4, previously it may be the E equal to 5. Now we want to make it equal to 5 plus 1. So we first locate the E4, and then traverse until the root, and update every information on the path we meet. So by doing so, we can find that besides this path, the most part of the program on the other black nodes, they will not be changed. And the time complexity will be OH, actually the tree head. Then let's see how we will handle the add operation. When we want to add a new node to CFG, actually we are inserting a new leaf to our API tree. So first is locating. Let's say if we want to insert the E5 after E4, how we will do. First, we will locate the E4. Okay, we will first find E4. Then make a left child of E4 as E4 itself. Then make a right child of E4 as a newly added node E5. After that, we made the semantic of E4, original E4, as a multiply. By doing so, we are adding a new node into the tree. But we can find that if we always add some node at some position, this tree could be imbalanced. So we also design some rebalance tricks like a weight balance strategy and a scalable strategy inside our data structure. Well, we will not discuss it here. You can refer that in our paper. So then let's take a look at delete operation. Let's see, we already added the E5, right? Now we want to delete them. So should we do a reverse process to identify E5, then remove them from the tree? Maybe we can, but it's very annoying. If you are deleting some nodes, there are many situations to discuss. Maybe we'll discuss the previous node and succeeding node. Or maybe the E5 could be the only one of a branch. There are many situations to discuss. To avoid this, we need to take advantage of a clean algebra property. So remember that we have 0 element, unity element, right? So let's say if we call the update process and set the semantic of E5 as a unity element, we will see semantically it's equal to the E5 is deleted. And also we do not need to discuss all these kind of situations. So within the clean algebra property, we designed 3 lazy rules for deleting nodes within these 3 basic structures. And also we will find that since we always inserting some nodes to our tree, but not actually deleting something from the tree could be imbalanced and it will keep going up. So we also design rebuild technique to sometimes delete the useless node from the tree to keep the tree size controllable. Now, let's see if the proposed method really works well in practice. So we have implemented our method in a tool, first using Zhou to generate a CFG from DaCapo benchmark, which is aligned with the previous paper, and it contains 3 real-world Java project source code. Since our method, Since our method is the first incremental API algorithm, thus our baseline are all non-incremental versions. One of them is a vanilla touches algorithm raised in the 1990s from the past problem. The second one is from OOPS 2023 paper, which used a graph tree decomposition and deployed a divide and conquer algorithm on each trees to compute the final result. So our experiments are designed to answer the following research questions. The first one is the most important one. Is our algorithm really that efficient, more efficient than the baseline? So the second one is that between our 2 technical innovations on the interpretation and on the past expression, which one contributes more to our incremental? The third one, how does the size of incremental changes influence our performance? So here is a result of RQ1, which shows that overall our algorithm is significantly speed up compared with these 3 non-incremental baselines. Because this baseline have some pre-process, and we do not need to do any process after we do the incremental. So every time if we call the pre-process to compute all things from scratch, it could be very time consuming. And also we test our algorithm on 3 analysis tasks: the uninitialized variable, the region definition, and the constant time execution. In all the 3 tasks, our methods has more than 100 times speed up comparing to the baseline. Okay, so let's answer RQ2. In all the 3 tasks, both our 2 parts are speed up comparing with brutally recomputing it. Here we can see as the tasks become more complex from the region definition to the constant execution. The more complex means that we are defining more complex abstract domain and more complex operators. Our method significantly saves more time, especially on the interpretation part. And the third, we also quantify the impact of a program changes to our algorithms. Previously in our traditional setting of incremental analysis, when the program changes effect goes up, it could be very slow. But as we can see, we incrementally increase our program changes from 2% to 20%, and the curve is nearly linear. This shows that the tree hit is relatively remain the same, and the time consuming is highly related to a tree hit. This shows that our method can generally keep the tree hit, and our rebuilding process is very useful. Okay, so for conclusion, we propose a new method for efficiently maintain and update incremental program analysis. Our methods have 3 new contributions on top of new non-incremental APIs, and our experiment shows that it really runs well. So, and that's all. Thank you for listening. I'm happy to take any questions. Thank you.
Thank you so much. So we have time for 1 or 2 more questions until we're heading over to lunch.
Hi. You talk a lot about control flow graphs. My question is if your method only works interprocedurally, or if it also handles interprocedural queries with like function calls like the other previous methods.
Okay, thank you for your question. It's a very good question. So in our experiment, as we are only raising a new algorithm, so we only do our experiment in intra-procedure. But actually, API can efficiently compute a summary of a function, like all the function will be an interpretation of a past expression. So it's easy for us to extend into an interprocedural setting. Thank you.
One more question?
Do you have a normal form for representing your expressions?
Sorry?
Do you have a normal form for representing the expressions?
I'm not sure, sorry.
Okay, I will explain.
Do you have a normal form?
Normal form.
For your expressions?
Actually, we can do that. I think there's a previous paper by Tom Raps. He did something to transfer it in a normal form. But actually, here for expression, we just drive it from the program itself. So we do not do any optimization. Thank you.
Okay. I think that's it for this session, and we're all hungry. We can head over to lunch. Let's thank our speaker again.
Okay, thank you.